Hi, my name is Rudrakant and welcome to this lecture on qubits and entanglement. Here we introduce the properties of single qubits and entangled qubits. Both bits and qubits are realized as actual physical systems. However, for the discussion here, we look at them as abstract mathematical objects. This gives us a freedom to define generalized qubit states and can be applied in any specific system for its realization. A classical bit has state either 0 or 1. It is like a coin, either heads up or tails up. What is then a qubit? Qubit also has these states. The three-dimensional sphere called block sphere provides a useful means of visualizing the state of a single qubit. Single qubit psi is represented by superposition of 0 and 1 states with coefficients alpha and beta. The main difference between bits and qubits is that a qubit can be in a state other than 0 or 1. It is also possible to form linear combinations of states called as superpositions. Alpha and beta are complex numbers. A qubit is a vector in a two-dimensional complex vector space. The special states 0 and 1 are known as computational basis states and form an orthonormal basis for this vector space. Unlike bits, where we can determine its state as 0 or 1, we cannot examine a qubit to determine its quantum state, that is, the value of alpha and beta. Instead, quantum mechanics tells us that we can only acquire much more restricted information about the quantum state. When we measure a qubit, we get either the result 0 with the probability alpha square or the result 1 with the probability beta square. Let us see how quantum information is processed. First, we prepare a system in a quantum state as denoted by psi in. We let the system evolve through a certain quantum phenomena to obtain a state psi out. When we measure the outcome of a system, the result will be either 0 or 1 when the wave function collapses. Until this measurement, the system retains its quantum nature. In geometric representation using block sphere, one can choose different bases like horizontal, vertical, diagonal, anti-diagonal, right or left-handed polarization. Generalized single qubit polarization is represented by psi theta phi. Quantum states psi parameterized by theta and phi is superposition state of horizontal and vertical components as shown on the right hand side. It is a combination of horizontal and vertical parts with coefficients depending on theta and phi. It must be kept in mind that there is no simple generalization of the block sphere known for multiple qubits. In two qubit states, we have four computational basis states HH, HV, VH and VV. A pair of qubits can also exist in superposition of these four states. So, the quantum state of two qubits involves associating a complex coefficient AHH, AHN, AVH, AVV with each computation's basis state such that generalized two qubit polarization state is represented as shown here. As an example of separable states, when two qubits in horizontal state exist independently, they can be represented together as psi separate equal to tensor product of states H1 and H2, As an example of entangled states, the qubits can be represented by psi entangled and are parameterized by coherent superposition of HH and VV states of the qubits. Such qubit state is known as Bell state or EPR pair. The Bell state has the property, upon measuring the first qubit, one obtains two possible results: 0 with the probability half, leaving post measurement psi entangled equals to HH, and 1 with the probability half, leaving psi entangled equals to state VV. As a result, a measurement of the second qubit always gives the same results as the measurement of the first qubit. That is, the measurement outcomes are correlated. These correlations were subject of intense interest for many decades since the famous paper by Einstein, Podolsky and Rosen in 1935. It is an interesting paper with title as a question. It questioned the entanglement nature that explained the non-locality of quanta, which permits instantaneous action at a distance between two quanta. The paper says the description of reality given by the wave foundation in quantum mechanics is not complete. According to the paper, every element of reality must be represented in a complete physical theory. Element needs to have a value that can be predicted with certainty and exists independently of the measurement. Applying the limit given by the speed of light, paper says it is possible to separate the physical systems so that they do not influence one another. EPR showed with their definitions of completeness, elements of reality and locality that quantum mechanics is not a complete theory. EPR insights were taken up almost 30 years later by John Bell, who proved an amazing result. The measurement correlations in the Bell state are stronger than could ever exist between classical systems. He derived an inequality that can serve as a test criterion for local hidden variable theories. If the so-called Bell test is carried out on a quantum system that follows a local hidden variable model, the test criterion will be bound to a certain quantifiable value. In this case, this value is exceeded, that is, the Bell inequality is violated. The physical system does not obey local realism, meaning the non-local quantum description is correct. The maximally entangled photon qubit states are as shown on the slide. It is important to notice that Bell states form an orthonormal basis and can therefore be distinguished by an appropriate quantum measurement. Since the initial proposal from Bell is experimentally difficult to implement, we measure a different inequality proposed by John Clauser, Michael Horney, Abner Shimnoy, and Richard Holt, known as CHSH inequality. CHSH inequality can be used in the proof of Bell's theorem. It states that certain consequence of entanglement in quantum mechanics cannot be reproduced by local hidden variable theories. Experimental verification of the inequality being violated is seen as confirmation that nature cannot be described by such theories. That is, nature plays the dice. CHSH inequality is a constraint on the statistical occurrence of coincidences in a Bell test. Classical theory predict that a certain value S has an upper bound of 2, meaning S should be less than or equal to 2. When quantum theory is used to calculate the corresponding value, S exceeds the value of 2 with an upper limit of 2 times square root of 2. Practically, The S value is determined by measuring the coincidence counts at different polarizer settings in an experiment as shown below.